We owe our
Gravity is not a
understanding of
force.
gravity as a force of attraction to Sir Isaac Newton. In the 17th century, according to a very popular legend, Newton was watching an apple fall in an orchard. He noticed the apple fell exclusively downward, as if under the influence of a certain force, which inspired him to create the universal law of gravitation. Newton was able to explain the dependence of the planet's rotation around the sun due to the gravitational force between them with an imaginary experiment. If you put a cannon on a mountain and shoot a cannonball horizontally, it will fall vertically to the earth after flying a short distance. But if you shoot it with a very high force, for example, up to 4,500 miles per hour, the cannonball will always be in a state of free fall and will not reach the surface. According to Isaac Newton, this is the state in which our moon, and in particular all other planets, even outside the solar system, are located. This is how Newton came to the conclusion that gravity is a universal force for the entire universe, acting in the same way everywhere. Albert Einstein's general relativity. Almost 300 years after Newton's revolutionary discovery, Einstein introduced the world to his view of the concept of gravity in the general theory of relativity. GR was preceded by the special theory, in which Einstein described that space and time should be perceived as an inseparable phenomenon, such as absolutely everything in the universe moves simultaneously in time and space. According to GR, he explained that massive objects are capable of curving time and thus affecting other objects around them, and this curvature is gravity. While Newton's theory was based on a falling apple, Einstein imagined a person in a falling elevator to explain his idea. As he falls, he doesn't feel his weight, because both his body and the elevator are falling at the same speed. However, when the person is moving up in the elevator, he feels accelerated, and it seems that the floor is resting on him. However, if there are no windows in the elevator, then the person will not be able to tell what he or she is experiencing from his or her point of reference. Falling in a gravitational field or moving at a constant speed in a small region of time. In Einstein's theory, this is called the principle of equivalence. In fact, if according to Newton's law, a person falls down due to gravitational force, then according to Einstein's theory, it's due to the absence of a force that pushed the person up. That is, a person is affected by the force generated by the elevator floor, but it is not gravity. This also implies that we are always in a state of acceleration unless we're in a state of free fall or inertial motion from our point of reference. So then Einstein concluded that gravity and acceleration are one and the same, and therefore we're in a state of free fall until an obstacle appears in our path, which became the basis for understanding that gravity is not a force. This is a very unexpected statement. Let's take a closer look at the theory of relativity. So as we've already noted, according to Einstein, gravity is a geometric curvature of a four-dimensional time-space. Its property is not a force acting in space. One can simplistically try to imagine time as a two-dimensional drawn fabric in which massive objects like the planet and sun create funnels, but this is not quite the right idea. A better option is to imagine time as a three-dimensional grid consisting of lines geodesics along which planets move in free fall. They are massive enough to distort the lines along which any objects move. That is why it may seem to us that, for example, cosmic bodies are attracted to each other. The theoretical physicist John Wheeler explained this idea quite simply. Space-time tells matter how to move, matter tells space-time how to curve. Danish astronomer Jan Oort first noticed that the rotation speed of stars on the edge of such galaxies remains constant, although they should be moving much slower. The solution to this paradox is the hypothetical dark matter first described by astronomer Fritz Zwicky, which surrounds galaxies. According to current estimates, about 70% of the universe consists of 27% dark matter and 5% ordinary matter. However, although dark matter is an important hypothesis for explaining this phenomenon and many others, such as bullet clusters, its existence has not been precisely confirmed so far. The problem with Einstein's gravity is the inconsistency with quantum mechanics. The main problem between these fields of physics is that GR is based on the principle of causality, while quantum physics is based on probability. Therefore, GR cannot work at the level of quanta, and quantum mechanics cannot work at the level of macroscopic objects, since an observer will know where a large physical object is located and how fast it's moving. There's no superposition state for it. The only solution to this problem can only be to develop a new theory of quantum gravity that would explain the interaction of objects and fundamental particles simultaneously. Despite some problematic issues, Einstein's repeatedly confirmed gravitational model is still the basis for modern research, regardless of its age. We cannot say whether GR will suffer the same fate as the law of gravity, but the coordination of the model of the world according to the theory, along with other areas of physics, is necessary without understatement for the whole of science. So since we do not yet have a new gravitational theory, we can summarize with some confidence that gravity is not a force.
We usually think of gravity as a force between objects with mass. It's easy to see how this force works by stepping on a scale to see how much you weigh. The number on the scale represents the Earth's gravity on your mass, or your weight on planet Earth. When it comes to gravity in the cosmos, we can imagine the Sun's gravity keeping the planets in their orbits, and we all know about the strong gravitational pull near a black hole. The so-called force of gravity is easy to understand, and gravity might seem like a simple thing after all. But things are different in the current age, as we know now that gravity as a force is only a small part of a more complex phenomenon thanks to the general theory of relativity. But before we get into that, it's time for a little Physics 101. Everyone is familiar with Newton, who was a veritable demigod of physics during his time, and the story about the apple falling on his head. Well, that didn't really happen. The truth is, Newton saw an apple fall from a tree and was in a contemplative mood. At that moment, he wondered why the apple fell straight towards the ground, and not sideways or in another direction. He presumed that a force of gravity between two bodies pulled them towards each other with a magnitude directly proportional to their mass. In short, Newton believed an apple falls because a gravitational force accelerates it towards the ground. Newton probably thought there was something missing from his theory though, because it said he wasn't completely satisfied with it. This is because he originally thought of the force of gravity as a push, not a pull. Little did Newton know that he was partially right about this, but his theory of gravity was accepted as gospel, that the magical pull was an essential property of mass, the theory which withstood and obscured the truth for the next 400 years. That was until Albert Einstein, another formidable genius, came along in 1905 and presented his general theory of relativity while working as a Swiss patent clerk. His challenge to Isaac Newton's theory was either ridiculed or ignored completely, because his ideas seemed too radical to be possible. The famous experiment by Apollo 15 astronaut David Scott was done on the moon to test this theory. At the same time, moonwalker astronaut Scott dropped a hammer and a feather, and they both glide to the ground and impact the ground at the same time. The same thing would happen for any object regardless of its mass or its physical makeup. This is known as the equivalence principle. So why do the two objects fall together and land at the same time? It's because they're not falling. They're standing still, and there is no force acting on them. With Einstein's theory, gravity is not a force between two objects with mass. Instead, gravity is the warping of space and time in the presence of objects with mass, and without some force acting upon the objects, they will travel in a straight line. Einstein believed smaller objects are not pulled on by more massive objects, but instead the objects are being pushed down by the space above them, and that there is no such thing as a gravitational force.